Hello everyone, my name is Weiser. Today I'll be sharing with you the research I conducted this summer using planar tunneling spectroscopy, PTS, to characterize and evaluate whether ytterbium boron 12 belongs in a class of quantum materials called topological condo insulators, TKIs. YBB12 shows TKI signatures, however, this study hopes to at least aid in the discovery of a smoking gun evidence. First, topological insulators are a class of quantum matter that harbor topologically protected surface states with an insulating bulk. In this figure, there's a formed energy band gap between the valence and conduction bands. Now, if the valence band is full of electrons and we apply voltage, there's nowhere for the electrons to go. In other words, it's a trivial insulator. However, in a topological insulator, only the edge states are conducting. So we can view a sort of spin-dependent path which only the surface electrons can flow. This creates a topologically protected surface which is resilient to small perturbations. Now, we are interested in TKIs because we can form a useful quantum computing component which has the ability to solve very modern problems that a classical computer either cannot or would do so inefficiently. Classical computers use the bits in which there are only two states, on or off, while quantum computers use qubits which have infinite states. The current standard for quantum computing uses abelian qubits which suffer from decay, which we have a hard time keeping in coherence. TKIs, on the other hand, can form non-abelian qubits, which, due to their protective states, are resilient to decay, in which we have a much easier time keeping in coherence. Now, the research we did this summer is planar tunneling spectroscopy, which uses quantum tunneling to take measurements. In classical mechanics, a particle would have to travel over a potential barrier, but quantum tunneling allows a particle to travel through a classically forbidden potential barrier. In order to prepare our YBB12 for PTS, our lab has developed a method for crystal polishing in which the surface is smoothed to a roughness of only 5 angstrom. Now we take our smooth crystal and we subject it to an ion beam etching, which removes surface impurities and prepares the crystal for plasma oxidation. This creates our thin potential barrier for YBB12 electrons to tunnel through. We then deposit lead, which enables us to measure the tunneling conductance and also quantify the quality of the junction made. This is some of the data we've collected this summer, where this curve shows an increase in resistance as temperature decreases. This is typical insulating behavior, but it also has this saturation beginning around 4 Kelvin. Moreover, we see a conductance hump at -25 and -50 millivolts. We can attribute this to the opening of the energy band gap, which we have observed to start at roughly 200 Kelvin. This, in addition to the resistance behavior, is evidence that YBB12 is a condo insulator. However, we are also interested in the topological behavior. So along with this saturation at 4 Kelvin, there's a corresponding increase in the zero bias conductance beginning at 4 Kelvin. Furthermore, we can see that as temperature cools, the conductance rises to create a steeper slope. All of this in conjunction shows strong evidence of surface states. So to conclude, we've discussed how TKIs can be useful in quantum computing and that our PTS data has shown that ytterbium boron 12 is a condo insulator and likely contains surface states due to its topological nature. There are still some open questions regarding ytterbium boron 12, but unfortunately that's all for today. So I'd like to thank everyone for listening, and especially Dr. Wong Q Park and Mr. Arjit Gupta for their close work on this project. Thank you.